Hi, everyone. Thank you for coming. My name is Dmitry Chuyko. I work for Oracle in Java-C performance team. And today we are going to talk about one of the projects I'm involved in. It's about static compilation for Oracle Java. All right. We will talk about ongoing experimental project, about how the feature is implemented and why it's done so. It also requires some visible and meaningful changes in Hotspot, and we'll also cover that. Don't trust me, not a word that I say, but I'll try to say some meaningful words. And of course, you shouldn't think of it as something deterministic and any commitment to any release of Java. All right. So one small note. Who still uses Java 6? No. Don't raise your hand. Shame on you. Of course, yeah, using any version is fine, and of course you can stick to not only to Oracle, some other companies support all the versions, but official end of life for 7 was a year ago, and you're currently strongly encouraged to try JDK 9, and it already contains Jigsaw, so then you try, something will probably broke. And I think it's definitely a thing that broke your code, but well, that's our life. All right, let's start from the other end, from far, far away. Long ago, in the pre-computing era, some machines existed, and that even were not computers, but some calculators for farmers, etc. And they had their predefined programs. It also could be some musical instrument or something. From the other way, there was always a will to do some custom work using some machines. So you somehow automated those predefined behavior. What I'm trying to say here is that predetermined behavior and some dynamic behavior always coexisted. As well, always during past century coexisted interpreters and compilers that are ahead of time compilers and just-in-time compilers also coexisted. So what's the Java? What's Java itself? It's, of course, a language and a platform. And what's good at Java is that it has strict specifications. It has specification for language and specification for virtual machine. And we almost all the time talk about performance. I talk about performance all the time because I'm in performance group. And of course, everyone who uses Java faces some typical or not typical problems with performance. Some time ago, everyone blamed interpreter, but of course, it's not an issue anymore because we have just-in-time compilation. And interpreter also became faster, even if you use it. And almost in any time, you can run your older jar on some platform that supports necessary specifications. That's a very cool thing about Java. Yeah, it's a cool thing, but it's a cool thing for a user. For a VM producer, you should support that behavior. So it's hard, really, to support specification and to run something you even didn't ever see some user code. What's a Java virtual machine? It's itself a program. It's a code. It's written in some language. It's compiled. And it, as we said, it can and should be able to execute arbitrary bytecode, right? According to supported profiles. There are no limitations that you should throw away of any temporary helper things that you produce during execution of user bytecode as a VM. And you, of course, can emit native code, and almost VMs do so, and reuse the result. So how results can be reused? And are they reused in Hotspot? In Hotspot, we have just-in-time compiler. And Hotspot itself is a program, as I said, and it's written in C++, no matter. If you look at your JDK installation, you'll find some native libraries, some dynamic libraries, some executables, and of course, class library files like jars or modules, module images. In Hotspot, there are many modes. And that mode is set, then virtual machine is started. So for some modes, you just can't change it on the fly, for most of them. You select your garbage collector. You select how your pointers are constructed. You select sizes of different buffers inside the VM, how they are used, code cache, TLAB, etc. That just can be changed on the fly. And you start and work in that mode. And just-in-time compilation Hotspot since 7 has by default now tiered compilation. Then 2 native compilers and interpreter coexist. So you start executing code interpreter, then you count some counters and decide that you need to compile hot method. What you do actually? You do a compilation, fast compilation, supporting some basic counters to gather more statistics. When you get more statistics, you realize that you need to do better profiling. Then you add even more profiling points, gather more statistics, your code becomes more hot, and then you try to compile it with high budget, but high quality compiler C2 to make it go to level 4. Sometimes you just have no budget for that, or C2 just can't compile this method, so it goes to C1. It's a state where you just strip all your counters, all your profiling, and your method is compiled as C1 compiler. During that process, there are a lot of versions of the same method. You just can't keep them all in memory. Your memory will end up very fast. So you need to clean and to sweep that out, and to keep only actual executing versions of method. There could be a few versions of method executing, but you keep just ones that are alive. And of course, JIT compiler supports all modes for Hotspot. So there's no such situation. Then you have particular garbage collector that's not compatible with JIT compiler. It's nonsense. Yeah, and then you do JIT compilation. You are actually executing on some hardware, and you know your instruction set. So you start and use all supported features of your processor. All right. Actually, this talk is about problems that we're faced with, and the problems that can potentially be solved by static compilation. So let's talk about some workload that we execute again and again in many iterations. And such runs we can do a lot of times to see some distributions for each iteration times. So here's the plot, and you see iteration numbers going through from 0 to 45, and execution time for each iteration in milliseconds. Yeah, unfortunately, the picture looks quite small, so I'll just show you each thing. So what do we see here? Here are two lines. One line is for execution with regular default tiered compilation. And another line is for execution when we stop at C1, don't do level 3 and 4 and 2 profiling. So here are two plots. First thing is a very first iteration. So it's most left points, 2 points here for 2 plots. And here's the same information, also including interpreter. So it's a problem. You start execution of your code, and it's really slow, because then you really execute it in interpreter. And even then you execute it in tiered, it's still slow, because you see the difference between start of this line, any of them, and the end, right? So the end is a performance of very warmed up application. And the left is startup. Yeah. So not a big application, doing a single iteration of workload takes, for example, in tiered, it will take like 6 seconds. It can take 2 seconds or 1 second, but it takes 6. It's a long time in many business applications, and a big difference. And of course, we want to keep just the tail of that plot, right? We are really interested in having big performance from start, right? That would be very good. But how would we do this? I don't know. Let's also sum the time that is required to pass all that iterations. So here is the plot that contains 2 parts, right? The left part is shaded, and the right part contains just tails. The line between parts actually corresponds to tiered case. So warm-up ends like after 35 iterations or so. It's much smaller time for C1 because we don't do transitions, we just go to peak performance faster. So for C1, it will be like 5 or 8 iterations. And if we sum the time, so we do a kind of integration for this function, the difference will be very high. So you see the difference is 2 to 3x, right? And for interpreter, there's no problem. It just stays in same performance. It's very predictable. But performance of interpreter is not very good. You see the difference. Then we plot same thing, adding interpreter line. Everything else looks just very, very low. And yeah, and if you compare peak performance of C1 and C2, C1 is also relatively slow. All right, so let's build some cool trading system. Use some fancy framework, put some annotations, write a function that will make our robot alive. And then we'll fail, of course, because at the start of trading day, our code will execute an interpreter. Or then we go smart and apply some training workload. And yeah, it will, in the end, execute our training trades perfectly. But then something happens. It anyway will go to interpreter, and time for your operation will be much higher. We saw the difference. So then someone comes and says, yeah, we'll use just C++, and then you deal with all that spaghetti code and interpretation between systems. Yeah, of course, Java, C++ and C are not the only options to implement Java virtual machines. You can use any language, as we discussed. But then you face all that problems. You face startup problem, you face warm-up problem, and you face peak performance and time to performance problem, right? Because you both warm up and need to effectively transform both your application code and the code of virtual machine. So for the similar plot will be, of course, different. It will show worse time for interpreter and much worse time for bootstrapped code with committed or any kind of JIT compilation. Because first you need to bootstrap your JIT compiler. So, how could the ahead-of-time compilation help with these problems? It does. For startup, we can just precompile critical startup code. Like, we can precompile all initializers, constructors, etc. We can precompile code required for loading your jars or loading your classes in any other way. That's the code that executes on startup of any application, right? So yeah, we can precompile the critical code and reuse it. So when we start, we'll just take that code and won't spend time for JITing it, for gathering profile, etc. It will just work. What's about time to performance? We need to precompile critical code, but that's not a startup code. That's our business code, right? We need to warm up it faster. We don't, in this case, care much about startup time. We'll just instantiate all data structures, etc., relatively fast. And then, typically, we can spend a lot of time doing training workloads. That can be really long. And it's done just to trigger different parts in compilation process. We can just reuse the final result and go straightly to it. Additional issue here is, do we reach same peak performance? Because then we change the way that we go through all code transitions by JIT compilation. We should, or at least we would like to see the same peak performance as JIT compilation gives us. That's a technical task. Yeah, the answer most probably is no, because you can see any presentation about JIT compilation versus static compilation, and you'll see things like profile-guided optimizations, etc. When JIT, of course, has many advantages in runtime, but in many cases, performance could be comparable. Okay, what's with latency? So the main goal here is to avoid de-optimizations. And you may not care much about your peak performance and startup time. So it's a separate task. You just need to be very predictable. So you should warm up, and to get some code that just not being de-optimized and shows you same time for your operation. And for free, you also get benefits of code sharing and not doing a lot of CPU work for JIT compilation. You can save your hardware resources and your power consumption. And then you start, and even if you just don't do any more work, you can save some footprint by sharing code on startup. All right. Some solutions actually already exist. Approaches are different, and the approach that is used for Hotspot is also different from existing ones. First, we can just cache and gather statistics what methods are executed and dump their compiled code into some caches. Also, they can contain class data, etc. Another approach could be just producing executables, native executables, and shared libraries. In this case, JIT compilation exists only for ability to compile some dynamic bytecode that comes into your application. Yeah, and another one could be not actually doing ahead of time compilation, but doing ahead of start compilation before you execute your main code. You just reuse a list of methods that you need to compile and a list of optimizations that had been applied in some trial runs. you may just do your training load once and then reuse its results. All right, a hotspot. As we discussed, it would be good to get code, native code, that won't suffer from the optimizations. And that will have good quality. Probably it would be good to have it better than C1 and comparable to C2. For just-in-time, or for ahead-of-time compilation, we have no time constraints. We have a lot of time before we start our program, typically, unless we do a deploy every hour. And we need to support generated code in virtual machine. So those are top-level tasks. Unfortunately, using C1 and C2 compilers to get precompiled code is not that easy. And it still gives, in general case, the code that suffers from the optimizations. So the idea was to use another compiler. And this is a compiler written in Java, and it already exists. It's called Graal. It's a research project of Oracle Labs. But it's a research project, but it's already quite mature. It contains a lot of optimizations. It supports a lot of optimizations. And there are also frameworks for support of other languages to be compiled using Graal. It's called Truffle. And what's good? It's proven to work. And Graal VM is based on Hotspot. And you can actually try it, browse the code, etc. It's open. Moreover, it's proven to work for AOT in experimental VM called Substrate VM. The code is very, very clean and fluent, and you can easily understand many parts of it just by reading some annotations or the definitions. It's that easy. You can plug something into it. You can plug some custom steps for compilation or transformations, etc. And it can be used to fully compile your methods and to use type information that you need to avoid the optimizations. And as I said, it contains a lot of performance things. All right, so we have some compiler written in Java. And how does it interact with Hotspot? Because C1 and C2 are written in C++, and they are actually part of the Hotspot. There is now a brand new interface. It's a Java Virtual Machine Compiler Interface. It's a JAP that's already in JDK 9.3. So you can download source code or JDK 9 builds, early access builds, and try it. The feature is experimental and is still being under minor change under development, even though it's feature complete now. And here are just a copy-paste of JAP goals of this thing. So basically, what JVM CI allows you to do is to capture different events. The most important are compilation events, when you need to compile something, to access metadata, and to be a compiler to produce bytecode. So how it can be enabled? You'll just specify some flags, then you enable JVM side. It's experimental, and you can turn on a JVM side compiler if it's present in your runtime. In this case, yeah, we have Graal. I believe it's a line for Graal DM. And you select Graal to be a last level compiler. So it will play instead of C2 and produce bytecode instead of C2 for you. The JVM CI itself is used only for such pluggable compilers, not for existing ones. Yeah, it's similar to existing interface for C1 and C2, but it's not used for C1 and C2. The code has, of course, dedicated modules, relative sites. And then you look how it's plugged into a virtual machine. You'll see some familiar patterns, and you do some service discovery, intercept some events, and respond to some behavior. So it works very simple. Virtual machine has compilation queue. It gathers counters, etc. It decides, I need to compile that method with a last level compiler. And it goes to JVM CI compiler, does the compilation request. You have a call to this compiler. It accesses metadata using API provided by JVM CI. And then you just generate some chunk of byte data and return it to virtual machine. So it's that simple. Of course, besides of JVM CI, you have some private implementation, etc. But you interact using public interface. All right. So what's better? We have clearly defined public Java interface. So we can make a proxy for that interface. In this case, we can just create compilation server, no problem. All right. So let's return to ahead of time compilation feature implementation for Hotspot. It's an experimental closed implementation, but it works somehow. So how it works? There are a lot of modes for AOT code. So we discussed that solutions for our problems are different. And for different solutions, we need different code. Basically, here are several kinds of different modes. First, it's a mode of problem that to solve. So, do we use profiling or not? Profiling costs a lot, and if we need just something with predictable latency, we don't need profiling. We need our precompiled code. That's it. Otherwise, we need some profiling in precompiled code, and both profiling and actual business logic, their native code should be compatible with runtime they run in. That's determined by VM mode. So we should precompile our code using the very same VM mode that will be used and be executed. So like we should choose garbage collector and other important things. And Graal itself, and actually also the part that's in addition for AOT support, they have their own options that also require just different code that want to coexist in a single virtual machine. So what happens then we produced and try to use AOT code? It plays instead of interpreter, because we instantly can execute an AOT code and gather counters. So we don't need low levels of tiered chain. When we go to most detailed profiling with level 3, we need to recompile our AOT compiled methods. Then we decide that they should be actually compiled to latest level. We may not spend resources still gathering counters and fall back to AOT code also, while last level compiler actually compiles our method. It could be C2 or it could be Graal, etc. And it's much more simple for non-tiered case when we don't need any profiling and transitions. We just stay in AOT code, in good case, of course. And so what exists in case we use AOT code? AOT code lives as native code in shared libraries understandable by operating system. It's a very good way to offload some work and some optimizations of loading that libraries to operating system level. And operating systems do that good. Currently, only one configuration is supported. It's Linux x64. Yeah. And we target just a single module to compile. It's a core Java-based module. I think you probably know it. Yeah. And besides of that native libraries, you should have some support in your virtual machine to be able to interact with that code, to use it as a known method implementation, as a known compiled method for some method of some class. So it requires change in runtime. And to get that code, you need to compile it somehow and somewhen. And there's a new tool that does ahead of time compilation. And of course, you should specify your mode, and you get a separate shared library for your specified mode. And it can work with basically all the things that we are familiar with. Modules, class files, and just individual classes. And you should just specify a class path for that. All right, what's the output? It's a big shared library, and the most part of it can be actually shared, because it's just code. And it's really being shared between multiple processes that use same AOT library. Yeah, but small words about bright future. Possibly we all like one-click installations, one-click container deployments, etc. And yeah, pre-compiled libraries might help. So how could we be produced behind the scenes? It actually could be done with a new JLink tool. It's a tool for modular packaging. Then you can produce stripped JRE image that contains only modules that you actually use. unlike current approach, then you strip just a little bit the Java packager. And there could be a module for JLink that will create shared libraries for you. Then you deploy your application. So that's it. You can potentially solve your warm-up, startup, and latency problems using static compilation. It has been implemented as a closed thing for Hotspot. It works using Graal and JVM CI. It enables to produce native shared libraries that are used by VM. And that helps to bring a big new Graal compiler and its good features to Oracle Hotspot. That's all. Thanks.